Welcome to StarSync Tracker's learning series on calibration frames. Lights, darks, flats, dark flats, and biases. Light frames are the raw exposures taken of your target object. The image will contain several artifacts that we can address by utilizing calibration frames. Let me provide a description of the various calibration frames that can aid in cleaning up these artifacts. A dark frame is captured by taking a picture with your camera's shutter closed or the lens cap on, using the same exposure time and temperature as your light frame. This frame is used to record the noise produced by the camera's electronics, such as amp glow, often visible on the edges of the image, some hot pixels, and other fixed pattern noise. Flat fields capture which pixels do not record as much light compared to the others, for reasons like vignetting, dust, or differing pixel sensitivities. To create a flat frame, use your camera attached to your optics, ensuring it is in the same focus and position as your light frame. Point the camera at a uniformly bright, well-lit field, which could be a lit panel or the uniformly lit daytime sky. The exposure time for the flat frame should be shorter than your light frames, and the pixel values should be around 2/3 saturated. You can verify this by viewing the image histogram. A bias frame or dark flat is a frame that primarily captures the offset values of the camera and contains a small amount of fixed pattern noise. The offset is the zero light level value of the pixels. Similar to darks, they are taken with the shutter closed or the lens cap on. A bias frame is the shortest possible exposure the camera can perform, while a dark flat frame is a short exposure with the same duration as your flat frame exposures. Assuming you have proper dark frames, you only need one of these frames, either a bias frame or a dark flat frame, as they serve a similar purpose in image processing. From now on, we will refer to them as dark flat frames. To begin the image cleaning process, we'll start by subtracting the dark frame from the light frame. This step is essential as it helps eliminate the amp glow and other fixed pattern noise present in the light frame. Similarly, we can enhance the accuracy of the flat frame by subtracting the dark flat frame from it. This action will remove the offset and a small amount of fixed pattern noise specific to the flat frame, resulting in a cleaner flat frame. Having completed the subtraction of the dark frame from the light frame and the dark flat frame from the flat frame, the next step involves addressing areas of non-uniform brightness in the light frame. By doing so, we aim to achieve a more accurate and true image representation. To accomplish this, we take the resulting light and flat frames and perform a division operation. Specifically, we divide the light frame by a normalized version of the flat frame. This division process serves to enhance the pixel values that were initially artificially dim, thereby bringing them closer to their actual true brightness. In other words, this step helps to brighten those dimmer areas and produce a more faithful representation of the image. After utilizing the calibration frames, we have achieved a significant improvement in the image quality. As a result, the final image now better reflects and closely represents the true underlying data. Thank you for watching our video. I hope it gives you a better understanding of what calibration frames are and how they are used.